Hi, NA Physics. It's Mr. Neff here again. All right, this is going to be our talk about wave speed. Hey, what do you get whenever you ask a lemon for help? Watch to the end of the video and I'll tell you. So we're going to talk wave speed here today, and say you were on a spot where you could watch the waves pass you by. Maybe you were standing on a dock, maybe you were watching a sheer cliff on a river or something like this, and you could watch the waves pass along. Say this distance right here from this wave crest to this wave crest was 2 meters. I could say that easier, but I don't want to. I want to make you think of a vocabulary word. Let's say that for that disturbance to cover that 2 meters, it takes 5 seconds. Again, I could say that easier too, but I want you to think about the vocabulary word. Now, I'm marking this distance as 7 meters. This is the distance from the crest to the trough. I don't actually have a good vocabulary word for that, but I have a good vocabulary word for half of that. And so I'm going to ask, how long does it take that disturbance to pass by? Now, notice what I'm not asking. I'm not asking how long does it take the water to move there, because this is a wave, and so the water is just simply moving up and down. Truth is, it moves sort of longitudinally and sort of transverse, and so the water is actually going to go in more of a circular pattern. I'll talk about that again in a couple seconds, but the water's not making any progress. It makes some momentary progress, but then it's going to go back, and it's really just going to cycle around like this. Okay, so how long does it take for or how fast are the disturbances moving if it takes 2 meters to go 5 seconds? Do a nice job. Give this a good, honest try. I'll wait for you. Do 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 do. Yes, you're right. 0.4 seconds. How did we get there? Well, anytime we want to have a speed, we take the distance and divide by the time. And so I'm going to say that it was the 2 meters and divide by the 5 seconds, and I'm getting 0.4 meters per second for the wave speed. Now, if you notice what I did there, I didn't say wavelength before, but I could have. I didn't say period before, but I could have. And I took those two things and I divided them. And so you can see that the wave speed is the wavelength divided by the period. That's something that you'd want to know whenever you were coming in for an exam. Now, we all know that period and frequency are reciprocal ideas, and so you could write the exact same thing as wavelength times frequency. Hey, your chemistry teacher may have written frequency as the Greek letter nu, but you can see why I'm avoiding that, and most physics types avoid that, because if I embrace that, I would have V is equal to lambda times nu, and my writing is not good enough to for you to distinguish those two. And so instead of that nu, and it's nothing wrong with that nu, and I wouldn't mark it wrong if you did it, but I'm going to put an F there instead. So now I ask a similar question, and you might think this is redundant, but it really isn't. I ask, how fast are the particles moving? Now remember, the particles are just moving in place. And I just got done saying that they move in a circle, and I'm not telling you how far they move side to side, so we're just going to talk about in the y direction how fast the particles are moving. Now, you could take this one of two ways. Sometimes people think I'm asking for the average velocity, and if you are thinking about the average velocity in an integer amount of periods, then you'd say that that would be 0 because our displacement is 0, and I like the way you're thinking. You could also be thinking about average speed. And if you think about average speed, that's going to be distance divided by time. And so, of course, distance divided by time is going to be, well, think about what it does in this y direction. It goes 7 meters and 7 more meters. And so it's going to travel 14 meters in the 5 seconds. And that looks like that's going to be 2.8 meters per second. So this isn't always the case, but in this case, the particles themselves are moving with a much greater average speed than the disturbances are moving. We're going to talk radio waves now, and radio waves are a kind of electromagnetic wave. Now, as you know, electromagnetic waves, anything on this visible spectrum, whether it's a radio wave, a microwave, visible light, X-rays, any of it, it all travels at the speed of light. And so that speed, Einstein called it c because it's a constant, 3.0 times 10 to the 8th meters per second. Sometimes you'll see that in kilometers per second, and so it would have been 10 to the 5th. But for our purposes, 3 times 10 to the 8th meters per second is a good thing to know. At a radio station, they're going to broadcast on a certain, well, to the average person, they just say, well, there's a certain channel number. But we know this as the frequency. Now, here in Pittsburgh, popular channel is WDVE, and WDVE is 102.5 on the FM dial. And whenever we have FM, that is an abbreviation for frequency modulation. We know that that number is in megahertz. Megahertz. Mega, as we can remember, is 10 to the 6th hertz. And so I look at that 102.5 and I know the frequency is 102.5 times 10 to the 6th hertz. So there's my frequency. And if I know that the wave speed is 3 times 10 to the 8th meters per second, then it's pretty easy to calculate how long these waves are. Everybody has a little different impression of this. Some people think the waves are teeny, teeny, tiny, and some people think that the waves are really long. Answer somewhere in between, actually, because if I say that the wave speed is the wavelength times the frequency, or the wavelength is the wave speed divided by the frequency, I could take my 3 times 10 to the 8th meters a second, and I can divide by my 102.5 times 10 to the 6th hertz, which is 1 over seconds. I'm writing it so you can see how that cancels. And I'm getting an answer of 2.9 meters. So pretty long, but not mega long, but also not mega short either. Nice, happy medium. Now, we won't go through another example, but I will say sometimes in class, I would ask, well, what about an AM station like KDKA, something we're proud of here in Pittsburgh? If you can see this old image I found, KDKA can be found at 1020 on the AM dial. Now, AM stations are kilohertz, and so that's times 10 to the 3rd hertz. If I would make this denominator smaller, then of course the answer is going to come out larger. Notice I didn't make it 1,000 times smaller because this is 1,020 kilohertz, and this is 102.5 megahertz. I picked two channels that are not the same but close to each other. Really, you can see that it's only different by a factor of 10, and so you could see that the answer would come out to a factor of 10 different as well. Here we have an example where we have two waves shown amplitude as a function of position. This is not as a function of time like you might be used to seeing, but as a function of position. And they're asking here, using the data in the drawing, determine the wavelength of each wave. Since it's a function of position, I can say that the wavelength is just how much distance is covered by one vibration of the source. So think about that vibrating pendulum that produced this, or that simple harmonic oscillator that produced this. Well, it vibrated one time while the wave traveled 4 meters. And so 4 meters for the blue one. And then the orange one, we can say, well, it vibrated one time, and it's vibrating a lot farther to the side. We'll talk about that in a second. But it vibrated one time while the medium moved 2 meters. It says the speed of the waves is 12 meters a second. Calculate the frequency of each one. So this is similar to what I just did. I'm going to say that the wave speed is wavelength times frequency, or frequency is wave speed divided by wavelength. And so I can take my 12 meters per second and I can divide by my 4 meters to get 3 hertz. Or I can divide it by my 2 meters to get 6 hertz. When I say 3 hertz, I mean that it does 3 cycles up and down every second. And that's what the wave is doing. That's what the vibrating source was doing too. 6 hertz, 6 cycles per second. Now, the part C, what's the maximum speed for a particle attached to the wave? Now, each one of these particles, whether it be a particle at this location or whether it be a particle at this location or this any of the locations, remember, they don't make progress side to side. In this transverse wave, they are moving just in the up and down direction, in the y direction, vibrating there. And so what's their maximum speed going to be? Well, that maximum speed is going to be right here at the center. And if you can remember back from simple harmonic motion, we said maximum speed was 2 times pi times the amplitude divided by the period. And so I could say that that's 2 times pi times, for the blue wave, an amplitude of 0.25 meters, and divide by a period for the blue wave. Now that would be the reciprocal of 3, and so 1/3 or a third hertz, and that would give me a 19 meters a second. Whereas if I put the red one in there, 1/6 hertz, 4.7 meters per second. An interesting thing our book brings up is the speed of a wave on a string. This is important to us because we like musical instruments, and there are tons of stringed musical instruments out there. The wave speed on a string it could be calculated by doing the wavelength times the frequency, and we will do that, but it is caused by the tension in the string and how thick the string is. And so it's going to be caused by that tension in the string divided by how thick the string is. Sometimes they'll call this the linear mass density and give it a Greek letter mu, which is not to be confused with coefficient of friction. And that way we can take the square root of that fraction, we can figure out the wave speed, and then from that we could know what frequency and wavelength would be allowed.